Good morning to everyone. In our previous video, we are seeing the derivation of characteristic impedance. Okay, so characteristic impedance for lumped models as well as for the distributed model. Right now, in this video, we are going to see how to derive the propagation constant. Here, propagation constant, first of all we have to understand the definition. If you understand the definition, then we can easily solve out the derivation. So propagation constant, okay, propagation constant is nothing but the logarithmic equation. Okay, so log of the ratio of the sending end to the receiving end current. Okay, so either you may say this in this way, the ratio of sending end to the receiving end to its logarithmic value, we say that it is an propagation constant. So first of all, whatever the distributed model is there, we are considering the same model. Which is having the load impedance as Z0 and your input impedance as Z0, which is excited with an voltage source. We know one value, the sending end current is Is and the receiving end current is Ir. So whatever the current flown through your middle branch, so obviously the difference of these two. So I can assume that the current flowing through your Z2 as Is minus Ir. Okay, so I am not considering the entire session, I am just considering an outer loop. So here I am just considering this outer loop. In this outer loop, please try to observe carefully. The current flowing through your Z1 by 2 is Ir, Z0 is Ir, and what about your Z2? Is minus Ir. Here all are drops. Okay, all are drops. So I am simply assuming the loop equation. So here if I am considering this, so minus for representing the drop, I am just considering the minus sign. So minus Ir into Z1 by 2 minus I0 into Ir. Okay, minus I0 into Ir. And here to represent the current direction, for this current direction, okay, whatever the assumed current direction, this Is minus Ir is opposite. So obviously it is considered as negative. So negative of negative, it becomes positive. So plus Is minus Ir into Zs. I think you may hope understand this. So the current direction here, it is draw downwards. So it is plus Is minus Ir, but my assumed direction is negative of it. So I can write this minus. So opposite direction. This minus represents the drop and this minus represents the direction of the current into Z2. Okay, so minus of minus, it becomes plus. Hope you may understand this. So I have the two terms, Is and Ir. So try to bring it out common and separate those terms. As per the definition for the propagation constant, Is by Ir, so propagation constant will be equals to Is divided by Ir. Okay, so I just rearrange the terms in such a way that e power gamma, I can say that propagation constant as gamma, e power gamma equals to 1 plus Z0 divided by Z2 plus 1 Z1 divided by 2 Z2. So if you rearrange the elements, you can understand how we got this expression in So now this I done for only for a smaller session. If I extend for the entire transmission line length L, so instead of considering for a simple z1 z2, I should consider for z1 of L for the entire length. So e power gamma L will be equals to, you multiplied z1 with into L, z1L and z2L. So if you replace your z1 and z2 values, you will get this expression. Okay, so once you got this expression, try to rearrange the elements. So you have to cancel over this g plus j omega, so it will become root over g plus j omega L. So please understand, this L will be in outside the expression. So now this will be equals to your e power gamma L. When you go for your exponential series, so as per your, I think, M2 or M3, you have the series the sin x series or tan x cos x series. Similarly, if you may understand the exponential series, which will be equals to 1 plus gamma L plus, for example, if I go for the e power x, it will be equals to 1 plus x square divided by 2 and x3 divided by 3. So likewise I can get, okay, I think it is. So you can have this expression. So replace x with your gamma L and find out the infinite series. So for higher powers, okay, so already in our characteristic impedance we see that for L is approximately equals to 0, if then L square will be also negligible. For smaller length, if you square it, again the value will be much smaller. So we can eliminate the higher powers. Similarly, we are assuming here also, we are eliminating the higher powers and comparing the your e power, exponential series up to 2 terms, power of 2. So compare your equation number 1 and equation number 2. From this, the first term is same, 1 itself, and the which is having the multiplier of L, it is having this. And if you go for the L square expression, this will be the value. So I can say that by comparing the values, gamma is nothing but root over r plus j omega L into g plus j omega c. So by comparing this, I can give the expression of gamma, that is nothing but your propagation constant, as root over z1 into z2, or you can say that r plus j omega L into g plus j omega c. Friends, please understand here, the main concept of this is nothing but we are trying to draw the derivation, we are trying to draw our secondary constants. Secondary constants nothing but your characteristic impedance and propagation constants in terms of primary constants. So already we got the z0 in terms of R, L, G and C. The same thing happens here also. Your propagation constant, you are getting the relationship in terms of secondary constants. Okay, so up to this, the derivation of propagation constant is completed. Okay, the derivation of propagation constant is completed. So for further secondary constants, nothing but your phase constant, attenuation constant and phase constant, that is alpha and beta. So if you want to try to solve out those rest of two parameters, those two things will nothing but equals to your propagation constant. So the relationship between your propagation constant and your alpha and beta will be given as gamma equals to alpha plus j beta. Okay, I know the value of gamma, so which is equals to root over r plus j omega L into g plus j omega c. So this is the value. So now we supposed to find out what will be your alpha and beta. So for this I can go for either both polar as well as rectangular models. So from this expression, the first step is I just remove this square root by squaring on both sides. If I square on both sides, the expression will be in this format. Okay, I have this expression. So try to elaborate this expression. From this elaborated expression, from alpha square minus beta square, if I compare the real and imaginary values, I can get the real value as alpha square minus beta square is equals to Rg minus omega square Lc. You may consider this alpha beta value also, alpha beta value as omega Rc plus omega Lg divided by 2. You have the alpha square minus beta square value, alpha beta value. But if I want to go further, I need to solve out the alpha square plus beta square for further my calculations. Instead of that, try to leave this one up to here by considering the real value. For alpha square plus beta square value, you just simply go for the polar format. So for polar format, we need to find out the magnitude of your expression. Okay, magnitude of your expression. How we are calculating the magnitude? For example, if this is my expression, okay, if I need to find out the what will be the polar equation, modulus of value, how we are going to perform alpha square plus beta square. The same thing we are repeating here also, but the value will be, what will be your gamma? Gamma value will be equals to square root of r plus j omega L into g plus j omega c. Friends, please observe here, I need to find out the polar format of gamma, so modulus of gamma. Now in the under the square root element, I need to find out the modulus value. So here please observe, for the modulus of any value, real value square plus imaginary value square, for that you have another square root. So for real value square r square, imaginary square value omega L whole square, and for this one we have the square root. So I just take this one as square root 1 by 2. And similarly here also we are performing g square plus omega c whole square whole root. So now instead of placing a double root here, I just take it out this square root on other side. So gamma whole square, and you know another equation, square root of a into square root of b is nothing but square root of ab. So right now I am just considering the same thing and I get the value. So now the square root of gamma square, is nothing but, okay, the square root of gamma square is nothing but, because here I am considering the modulus of gamma. So as the square root of, I just bring out here, it will be alpha square plus beta square. So alpha square plus beta square is nothing but, this is the expression. So I get the value of alpha square minus beta square and alpha square plus beta square. We have the two equations and two unknowns, either by addition and subtracting, both by doing addition and subtracting I can get the values of alpha and beta. So now the same thing I am going to perform right now. So I am just simply adding these two, expression 3 and 4. So when I add two expressions, I can get 2 alpha square on my left hand side. So simply add these rest of two elements on right hand side, I can get alpha value. So I just first take it the common 1 by 2 for the whole expression, and for that it is square root. Again for the whatever the beta value, subtract the element, you can get minus 2 beta and the rest of the element. So to eliminate the minus, I am just interchanging the terms and take the take the 2 on another side and have the square root. So this is your attenuation constants, which is measured in Neffers, okay, which is measured in Neffers, and this is your phase constant, which is measured in radians. So till this we completed the derivation of secondary constants in terms of primary constants, okay. So in our next class we are going to see how to perform a numerical, okay, how to solve a numerical based upon these expressions, okay. Thank you.